The topic is designing of synchronous counter. In this topic, we will learn to design any random synchronous counter which can count anything. Maybe a skipped value, maybe even counting, maybe odd counting, etc. So we will learn this topic with the help of examples. To start the topic, first of all, there are two types of sequential circuits. First is Murray circuit and the second is Mealy circuit. Murray circuit is the circuit in which output depends only on the present internal state. Whereas what is a Mealy circuit? In which the outputs depend on both present state as well as the inputs. So let us start the topic with the help of examples. The very first example that I have taken is design a 3-bit gray code counter. So a 3-bit gray code counter is going to count gray codes. First of all, we are going to start this topic with the help of steps, and side by side we will learn the procedure as well. To start the topic, first of all, step number 1. So what is step number 1? Step number 1 is state diagram. As you can see it over here, these are the state diagrams. So what is a state diagram? A state diagram shows the progression of states through which the counter advances when it is clocked. That means the sequence. First of all, I have designed over here a 3-bit gray code truth table. Now I hope everyone remembers how to convert any binary number into gray code. So this is gray code of 0, gray code of 1, gray code of 2, gray code 3, 4, 5, 6, 7 and then recycle condition. Now state diagram. State diagram is nothing but the representation of the next value with the help of truth table. So you can see it over here, starting from 000, then we have 001, 011, then 010, 110, 111, 101, 100 and once again the recycle condition. So this is how you can design the state diagram of any random truth table. Now step number 2. Step number 2 is known as the next state table. That means now you have to design a truth table between the present state and the next state. With the help of state diagram, we can easily design this. First of all, I have mentioned over here all the 3 outputs Q0, Q1 and Q2. The same truth table, that is a 3-bit gray code. You can see it over here. The same truth table I have written over here once again 0, 1, 2, 3, 4, 5, 6, 7 in gray codes. Now what is the next condition? The next condition or the next state can be written with the help of state diagram. So first of all, for 000, what is the next state? See the state diagram, 000, the next state is 001. So the next state is going to be 001. In the same manner, you can just fill this present state versus next state truth table. Now I'm going to talk about the next step, step number 3. Before that, just a revision, quick revision about the excitation truth table of JK flip-flop, because we will be using the same for the implementation of step number 3. The excitation table of JK flip-flop is Qn, Qn plus 1, 0001, 1011. The value of JK will be 0 cross, 1 cross, cross 1, cross 0. This is also known as transition truth table. Now, step number 3 is flip-flop transition table. Now, once again, I have written the same truth table which we have already discussed in step number 2, which was the truth table for present state and next step. So this is exactly same. There is no change in that. Now as we are going to implement a 3-bit gray code convert counter, so we require 3 flip-flops, flip-flop 0, flip-flop 1 and flip-flop 2. So we have 3 flip-flops, JK flip-flops. First of all, how to write down the value of J0 K0? This is only done with the help of excitation truth table of JK flip-flop. To write down the value of J0 and K0, we have to consider the value of Q naughts. So consider the present state as Qn, next state as Qn plus 1. For 0, 1, the output is 1 cross. For 1, 1, the output is cross 0. Similarly, you can fill the table. On the other hand, how to write down the value of J1 K1? Now you have to consider Q1s. So present is Qn, next is Qn plus 1. Compare the values. For 0, 0, 0 cross. For 0, 1, 1 cross. Similarly, you can fill the table. And finally, J2 K2. So we have to consider Q2 from present state as well as next state, and in the same manner we can just fill the table for J2 and K2. Now once we have got the values of J and K for flip-flop number 0, flip-flop number 1 and flip-flop number 2, now we have to calculate the values of J0 K0, J1 K1 and J2 K2. So that means now we are in a need to calculate total 6 values. So step number 4 is K-map. We can easily use the K-map for the calculation of output values. We have to design 6 K-maps for all the 6 values. For J0 K0, for J1 K1 and J2 K2. And we will be implementing the K-maps with the help of present state values. Now, in the present state, I have 3 input signals. So we are in a need to design a 3 variable K-map. So this is a 3 variable K-map. You can see it over here. Now, how to fill the value? First of all, 0, 0, 0. This is block number 0. So in block number 0 for J0, I am going to fill 1. 0, 0, 1. This is block number 1. Now 0, 1, 1. This is block number 3. 0, 1, 0. This is block number 2. So we have to fill the blocks as per the given values as a binary numbers, not as a code number. So next is 1, 1, 0. This is 6. So in block number 6, I am going to fill 1, 1, 1, 1, 7, 1, 0, 1, 5 and 1, 0, 0, 4. So this is how you're going to fill your blocks for J0 and then for K0, then for J1, K1 and J2, K2. So these are the K-maps that I have designed over here by taking the values in consideration from the previous slide. Now the next step is simplification. That is K-map simplification. Now first of all, to calculate the value of J0, you can see it over here. We have only 2 possibilities, that we can have 2 groups, 2 pair groups. So J0 comes out to be, first of all, the answer of this group. So this is 0, 0, that is Q2 bar, Q1 bar, and here both the values are changing, so we are not going to write down Q0. Similarly, the answer of this pair 1, 1, so Q2, Q1. So this relationship is nothing but XNOR gate. So this is Q2 XNOR Q1. Similarly, K0 comes out to be Q2 XOR Q1. J1 comes out to be Q2 bar dot Q0. K1 comes out to be Q2 dot Q0. J2 comes out to be Q1 dot Q0 bar, and K2 comes out to be Q1 bar dot Q0 bar. Now last step is step number 5th, that is the logic expressions. So this is from the previous slide only. We have already calculated these values in the previous slide, so this is just a sum up for that. And the final step is counter implementation. First of all, you need to draw 3 flip-flops, the basic ones, FF0, FF1 and FF2. Then you have to give the same clock signal to all the flip-flops. and afterwards the connections. So the connections will be, first of all, J0 is Q2 XNOR Q1. So J0 is, you can see now these values, this is Q1 and this is Q2. So Q2 and Q1 over here through XNOR gate and here through XOR gate. So you can see XNOR and XOR. Similarly, the value of J1 and K1, you can implement it. Although you may find this clumsy, but you can design the same by yourself. It will give you much more clarity about the circuit implementation. So this is the value for J1. So J1 is Q0 and from here you can see the signal Q2 bar. Similarly, K1 and J2 and K2. So these are the values we have taken from the previous slide, the values, and just inserting with the help of proper connections. You can simplify, you can take a lot of examples which are available in the book, and you just need to follow all these exact same 6 steps and you can implement any random synchronous counter.